to start this off by saying I invited you under technically false pretenses.
Okay, that's fine.
I invited you over, Casey, because I actually just wanted to hang out and I needed a technical topic to get you to agree to. And so if you want to talk about ARM, you can talk about that, but you can also tell me about anything. And if you have anything technical to talk about, I'm in.
Well, I love being on the show. You could have just said, "Hey, come talk about anything. Come listen to me talk about WordPress," and I would have said yes. So thanks for the invitation.
Yeah.
But I'm happy to talk about ARM if there was something in particular that you or your viewers were interested in that I can help with. I mean, I'm not an ARM expert, obviously. So if it's something highly technical, like, hey, this particular ARM instruction, I'm going to be like, sorry. But if it's sort of more just about ARM in general, I might be able to help. But if not, we can, yeah.
How about we just ARM versus Intel or ARM versus RISC-V, CISC-V?
Okay, sure. CISC. Did you just call it CISC-V? I like that.
Yeah.
Well, sure. I mean, I guess the thing I would say is we sort of touched on this a little bit back when you and I did that stream on there's a person who's like x86 needs to die.
Yeah, I remember that.
Was what it was, yeah. And kind of it's a broader topic than what that person was talking about, but it came up there, which was just that people believe that ARM is like intrinsically better for lower power, devices that don't consume much power, that performance per watt, whatever you want to say, right? That's the conventional wisdom. Like ARM is better for low power, and Intel is not, just inherently. And a lot of people then you can literally, like, if you Googled that, you'd find on Stack Overflow and stuff like that, or Quora, you'd find people giving reasons, and those reasons just aren't accurate. Maybe they were accurate for like ARM 1, like the very first ARM processor, which was like back in the BBC Micro days. It's like it was designed as a successor to like the BBC Micro computer, for people who know what that was. But we're talking ancient history at this point. But nowadays, a lot of the things that they say just aren't true, right? ARM is not a small instruction set anymore. ARM's a huge instruction set at this point. And calling it a reduced instruction set is really hard to justify, and so on. So, maybe what we could do here is just give people a little bit of perspective about what the actual difference between these two instruction sets is. And then maybe just a vague notion of like why ARM has been better for power, which I think is not really the reasons people think. I mean,
I think there's a lot of good places in here to go.
Okay.
I think a lot of people don't even, honestly don't know much of a difference between ARM and x86. In my head, it's just two different instruction sets attempting to do the same thing. I'm not really sure if there is much of a difference besides for like ways to just, this one uses this set of instructions, this one uses this one, and that's that. But I have a very black box understanding. And then on top of that, the power thing's very compelling because I know Sushi Dragon, if you've ever seen his streams, he does these really amazing...
What's Sushi Dragon?
Sushi Dragon is this live stream editor that does a lot of AI and stuff to just completely morph a bunch of his streams. And he's been able to skyrocket his power by adopting computers that use ARM as opposed to x86. And so he does all of his streaming now off of like MacBooks, as he used to do it with Lenovo or some run-of-the-mill company.
Well, maybe we'll just do this, because people seem to, when I'm on the show, people generally expect there to be some weird technical stuff. So maybe we could start there, because that's, you got to give people what they want. That's how I think of it.
Yep, I'm on that team. Let's do it.
So maybe let me see if I can do this here. If you want to make me big, I will make my head small.
Gotcha. Give me 1 second.
I can show you some literal just to give some literal examples here of what's going on with things.
I gotta make myself small. I just realized I'm giant. I'm over here just focusing on.
Oh, that's okay. We don't need that. We don't need that.
Huge.
You can stay giant. You can stay giant. It's okay. We're only using the top. We're gonna use the top here. So. Can people read that? I don't know if can I make this larger? I think I can.
Yeah, some of the encodings, because this is going through several encodings. So it might
Let me
be.
see if I can make this
Uh,
larger and still see it. Is that big enough to see? Maybe I'll go one more. I think we got enough room for one more. Just real large. All right. Maybe people can see that.
People are saying it's good. I'm trying to figure out
Okay.
a way to. There we go. Perfect. Okay, I can see this.
All right. So for those of you who aren't, I'll just quickly say, for those of you who aren't familiar with this tool, there's a fellow named Matt Godbolt. I think he was a Google engineer. I think, I don't know. I don't think he is anymore. He might be retired. I'm not sure. I don't know where he works now, but he made this tool. It's very famous and popular among people who like to look at low-level code stuff. And it's freely available. It's just called godbolt.org here. It's called Compiler Explorer, and it's at godbolt.org. And what it lets you do is it basically just automates the process. For any given compiler that actually compiles to machine code, you can usually do a thing with the command line of that compiler or with a disassembler or various ways to get out the actual assembly language instructions that compiler generated for your high-level code.
Okay.
And the problem is, a lot of times, you just don't do that when you're programming normally, even if you're someone who reads assembly language fluently and would be interested to see. A lot of times you just don't bother with that because it takes too long to go through that process, and it's annoying. So this automates that process, and more importantly, because what you can do, like what I do a lot of times, is I step through stuff in the debugger, and that lets me see the assembly language code very quickly, but only for one compiler. And so what this tool lets you do is it lets you put in some source code into a window. And I'm sort of this is the source code here. This is a simple C program. Probably everyone could read this. It would be legible in every language, basically, right? It's like, I'm going to multiply two numbers together. This is just the default that comes up when you start Godbolt. But you can put anything you want here. And then over here, you can add as many. I've created 3 windows here, but you can add as many windows as you want and pick compilers from a huge set of compilers for various platforms. Like here I've got x86 64, GCC 14.2. Then I've got ARM GCC 14. I don't know why I picked 1 there. I meant to pick 2. 14.2. Here I've got ARM 64, GCC 14.2. And it shows me the assembly language that's generated for each of these compilers and platforms. Now, this is just a great resource for people who want to investigate this stuff because it's so fast, right? If I want to see like, oh, I just want to see what happens if I just return num, like instead of multiplying, it takes a little bit, but then it updates the other windows. So it's like, it's very dynamic. And it's like, especially if you're someone who's just learning assembly language, it's pretty great because you can just put anything you want in that left window and quickly read what it comes out to be in other, in the other windows. And it just helps you gain this intuition for what's actually going on.
This is incredible. I mean, I've seen Godbolt before and I've used Godbolt, but for those that haven't used it, first off, I can't believe a man was named with the last name of Godbolt. Like, life is unfair, truly. But then on top of it, like, this is such an amazing tool. Like, the amount of time that I had to spend in 2005 looking up stuff to understand what's happening during my education time is just like, man, I wish I had this back then.
Oh, and there's way more features than I'm talking. I'm only just briefly interested, but there's tons more features. If I move over this, it tells me what the instruction is, right? I mean, it's fantastic. And the amount of time, like to your point, that you would save if you were trying to learn about something like this it's just phenomenal. So it's a fantastic tool. Everybody loves it. Everybody loves Matt for making it, and here it is. Now, the thing I would mention here, again, just for people who aren't familiar with this, is that, why do we care about the assembly language code? I'm going to show you some things because we want to know about ARM versus x64, so maybe that's one reason you care. But more broadly, why do we care about assembly language code? Well, some people think we care about assembly language code because that there are these, ancient wizards who still program in assembly language, right? And that's the only people who care about assembly language. And they think that, you see this come up sometimes in arguments where people are like, you shouldn't use such and such a high level feature because it creates this really bad code or something. And people are like, yeah, well, why don't we just all program in assembly language or something?
Yeah.
This is an antiquated view. It's just not how the world works anymore. Almost nobody programs in assembly language. There are a few times, very specific times, in very specific circumstances or very specific domains of embedded programming or very specific domains of optimization where you may have to program assembly language. It does still exist. I don't want to say that it doesn't. But the vast majority of people who do performance work don't ever actually program in assembly language. But what they pretty much all do, if they're good performance people, is read assembly language. And that's kind of the real disconnect I think people have. The reason why you learn assembly language today, for almost everyone who learns it, is not because you want to write like by hand the assembly language. It's because you want to understand why something is happening, or you want to understand a weird performance thing that you've seen, or the most common now, because of the world we live in, security research. You want to be able to disassemble things and see what they're actually doing, and you don't have the source code, right? That's another huge one that wouldn't have been a thing 20 years ago much, right? But now, very much so. And so the reason that I think it's really important, when we go through this exercise, that people learn assembly language is because A, it's very simple. It's much simpler than your high-level language. It really can't do very much, right? It's a very basic, low-level thing. And two, it is the machine code that your hardware executes. So when you learn what it does, you are learning how the machine actually works, which is not true of any high-level language. High-level languages are always things that are, some kind of intermediate, where you're then going to turn it into this machine code. And the assembly language, by contrast, is almost one-to-one. There's a little bit, the machine code itself, we can talk, we're actually going to touch on that today. The machine code itself is a slightly different thing in concept, but it's more or less one-to-one. So if you see a particular assembly language listing, you pretty much know exactly what the computer is going to do with that. There isn't really an additional step that you need to take. So does that make good sense? Hopefully I've covered basically everything there. You didn't know to get started on that?
Fantastic intro. I think everybody is salivating and ready. It sounds like, if I were to put it in layman's terms, it sounds like assembly is kind of like learning the alphabet, like and all these like the basic, the very basic, the phonics of everything, very, very basics. Yeah. It's the doing the high levels, like putting those together and creating vocabulary where a small set of sounds now has a very large semantic meaning, which can still be broken down into a bunch of small set of sounds. Not that it's like a great one for one, but because, the semantic meaning is actually the important part, not the sound effects, but you get the idea.
But they're both important, right? And it's like, this is why, they had times when they stopped teaching phonics in curriculums across the country, and people had a really hard time reading, and they went back to phonics, right? There's sense. A reason why, it's really good to have an understanding of what the computer is actually doing. Again, not because no one is saying, especially not me, I almost never write assembly language, like hand type it in, right? But I'm constantly reading it because it keeps me informed of what the computer's actually doing. And it also unlocks all these other things for you, because once you know the assembly language, you can do things like read a CPU diagram, because CPU diagrams are telling you how the assembly is executed, right? They're not telling you how C is executed. They're not telling you how Python is executed. They're telling you how assembly language is executed, because that's what the CPU gets. And so it also unlocks all this other knowledge for you that you really can't have. It's meaningless if you don't know the assembly, because you simply won't understand what that diagram is meant to tell you. So amazing. So anyway.
Okay.
So if we take a look at a tool like this, which, again, thank you to Matt Godbolt for making such a cool thing and putting it online where it's easy for everyone to access. You don't have to install anything. You just pop on there. What I wanted to show was just some basic ideas about what the difference between these two instruction sets are, so that people kind of know what we're talking about. Because when we talk about ARM, there's multiple things that you have to consider. And when people say ARM versus x64 or x86, which they probably mean x86 64, which is the 64-bit version of x86. Remember, their legacy versions. By the same token, when people say ARM these days, they probably mean ARM 64, which is the most modern one, not ARM 32, although that is still in use because you may have 32-bit processors and like low power embedded, whatever. So again, these instruction sets come in various flavors. We're not going to talk too much about that now because it's not that important, but you have to remember that, when people say ARM or x86 or x64, there's a kind of those are umbrella terms. And if you really want to talk specifics, you have to sort of pick some things. But suffice to say, when we talk about those things, we're talking about what's called an ISA, instruction set architecture, which is basically a series of definitions of what machine code does. It's like, if you put these bits in memory and tell the CPU to execute them, what will the CPU do, right? And there's additional things on top of that, things like, how exactly are you going to handle, when you're talking about how these things will execute, it's not just, oh, what does this math operation do? Like, what does add do? It's also going to be things like, how is the security handled? Like, are there different modes the processor can be in where if you're in this mode, you cannot access these instructions because those are high security instructions. Only the kernel should have access to them. All of that stuff is contained in this idea of an ISA, an instruction set architecture, or ISA. So when people talk about that, they're talking about this broad specification that talks about how the instruction set works and all of the things that go with the instruction set, like the security model and the memory models and all of these things. But that's what you mean when you say ARM, because you're not, and the same with when you say x64 or x86, you're not talking about a particular processor, and that's very important. Intel and AMD have completely different processor architectures. So they're using the same ISA for the most part, although they each have maybe some slightly different extensions that maybe only are on their platforms. But for the most part, they're using the same thing, but they have completely different hardware implementations. It's important to remember that. The same is true for ARM. When we talk about some processor from Qualcomm versus like a Snapdragon processor that might be in your phone, or we talk about an Apple M series processor, which might be in your laptop, these are completely different architectures, right? And although they might share some DNA sometimes, because sometimes there's hardware architects that have worked on both of them, so even though they're completely different. In the ARM world, there may be a little bit more commonality. And the reason for that is because you can, when you license ARM from ARM, you also get a bunch of reference designs with that. And you may choose to use some of that reference design when you are making your chip. You don't have to, but you might, right? And so there also is a little maybe more shared DNA amongst ARM things, because even the hardware itself, you're getting some of that when you license ARM. You're not just getting a document that says, here's how the instructions work. So that's what we're talking about.
Okay. This great precursor, by the way. Now I feel like we're ready. We're engaged.
I'm sorry for so much warm-up. I just want to make sure everyone knows.
It's the perfect amount of foreplay. We're ready.
You can edit it out. So when we look at something like this, what I want to show you is when we're talking about these two different things, we're really just talking about some differences in how we are putting binary, like actual data, into the computer for it to execute. That's what we mean. And so when people make claims like ARM is better for low power, what they mean, or have to mean, maybe they're not intending to, but this is what they have to mean. They mean that literally this way of specifying the bits that control your CPU allows you to make a lower power device. Because short of that, it's a nonsense statement. Because the only thing that defines ARM and the only thing that defines x86 or x64 is that encoding. That's what you mean. So there can't be, it's not talking about a particular chip or a particular way of doing something in hardware. It's really important to remember that. So let's take a look at what's going on here. Over here, we have some source code. This is just the default that comes up when you start Godbolt. It happens to be the square thing. I deleted the times num earlier, as you saw me do, to show it change. But what you can see over here is we've now created the assembly language over here. Godbolt made it for us directly. You can see here we just have a function. It's supposed to return a number, and it takes a number, right? And then the only thing this does is return that number. It doesn't do any operations on the number. What we can see over here is that you get some code for what happens in these different platforms. And really, the differences are incredibly minor. They're so minor, in fact, that the only reason that you see a difference at all is because of the particular platform that this is compiling on. There's a thing called an ABI that defines how variables are passed and things like that. But for the most part, you see there's almost no difference between them. And specifically, what we have as the last instruction, there's always a thing that's basically a return, right? It's essentially encoding exactly what this does, which is return back to the function that called me, right? So you can see this ret here is that. This BXLR, this is actually branched to the return register, basically, which is the thing that holds the address that you came from, so it's effectively a return. And this in ARM64, there actually is just a return instruction again. So you see that's all the same here. And the only code that exists at all that actually does anything is here in this x86-64 version, where it has to move the location. This EDI is actually where the input parameter will come in. And this EAX is where the return value goes out. Just purely by convention, that is what this platform defines. And so it will do that move before doing the ret, just so you get the input parameter passed as the output. That's it.
And we can see the other ones do the other ones have to do something similar anyways. Is BX kind of, or BX in the next column over in the ARM32, isn't that kind of interpreted the same way? I don't, forgive my language if I'm using the wrong language, because something has to say this parameter now goes in the return slot. I assume it has to be copied somewhere.
It does not. And the reason for that is because, in keeping with our streams, I'm just I'll go down all kinds of rabbit hole.
I'll just ask questions that I find very intriguing, because I would just assume something has to say this is the return value.
Okay, so there's an additional thing that layers on top of this, and that is what's called an ABI, or Application Binary Interface. This has nothing to do with ARM, and it has nothing to do with x86-64. What it has to do with is which operating system you're on. Each one of these is implicitly on an operating system. We know that GCC is native to Linux, so I believe this will just be, I don't think you have to specify anything in Godbolt. It's just going to assume Linux, basically, and the Linux ABI. What this application binary interface specifies is things like when you call a function, and I guess I should mention just before that, there's no such thing as parameter passing in assembly language or to your CPU. The concept of passing parameters is entirely something that is native to the actual the definition of a particular environment that you're programming in. And so what happens is when you have a platform like Linux or Windows, or Mac for that matter, they define something called an ABI, or Application Binary Interface. And what that says is, look, if you have a function and you're trying to implement a function, compile a function down to machine code, here are the rules for where the parameters go. So again, we don't need to get too far into the weeds on how assembly language works, but basically these are things called registers. Registers are names that we give to slots, effectively logical slots that we're using for programming in assembly language. So, I'll just give an anatomy of an instruction. This is called the mnemonic for the instruction, and it basically says what the instruction is going to do. MOV is just the mnemonic, meaning the word name we give to a particular binary encoding that will tell the CPU to move something from one place to another. MOV makes sense, right? Then it has two things, which are the two operands for that instruction. And in this case, they're going to be, this is the destination. The destination comes first. You can think of equals it being the same. The left side is the thing that gets the value. The right side is the thing that gives the value.
Can I interrupt one quick second?
Please.
You told me what EAX meant months ago. I'm going to see if I can remember what it is. E is for extended.
Okay.
A is the first register. And X is like the extended first register. It's like a second set of registers because there's A, B, C, D, and then AX, A, BX, CX, DX. Do I remember this correctly? I know the E is extended. I know I'm close, but I'm not. It's not horseshoes.
Very, very close. So what it is just you were right. You just thought you needed a second thing, but there is no second thing because this is Intel, and they've gone through so many revisions of this architecture. The original register was A before x86.
Yep.
The original register was A. Then when x86 came along, it went from 8-bit to 16-bit. They added the X if you're talking about the 16-bit version of the register, right? So that's AX.
Hold on one second.
Then when they went...
Hold on one second.
Sure.
I got a little...
No problem.
I got a kid. I don't know what's happening. Hold on. You can entertain them for a second.
Okay, I'll entertain them.
I get it. What is it? Where is it?
I guess I don't know. I don't want to not answer Prime's question. Well, here's what I'll say. I'll just continue the explanation of this instruction so you can know. So what happens is there are no such things really as variable names in something like assembly language because the CPU is programming with a fixed number of like names for things. That's just how ISAs are defined. And so when you talk about variable names, you only get the ones they give you. And so in a more sane time, they'd just be called R0, R1, R2, R3, R4, R5, right? Through however many the processor had. But because of legacy reasons, they often have weird naming schemes that don't line up exactly that way. So the register names are just EDI here and EAX here. And again, some of that naming is just telling you whether they're 32-bit or 16-bit and things like that. And again, a bunch of details that would be worth going into if we were trying to learn assembly language here. But if we're just trying to gain the general knowledge of what's the difference between x64 and ARM, we don't need to go down that rat hole. So we can just think of it as, look, there are these names for sort of logical slots that we're programming with. We can move things between them. We can do operations on them. And these are some of those names. The names differ between instruction set architectures, obviously, because x64 has different, randomly ended up with different names for their registers than ARM. And so you can see ARM here, for example, has this LR register. That is not a register that exists on an Intel assembly. In Intel assembly language, you couldn't use that name to refer to something. So you get some differences in naming, but they mean the same basic things. And sometimes, like in this case, sometimes the registers have specific dedicated purposes where you're usually using it for one specific thing. And in this case, the LR is like specifically for holding the address of whoever called you. So that is why it's kind of got a more specific name. I don't think Godbolt, it doesn't look like Godbolt can explain that part to you. It doesn't seem to explain register names. So it does, like I said, give you, if you hover over these, you can find that out. But if you want to know more about the different registers, you have to look at the actual architecture manuals. But sorry, is Prime back? I don't know.
I am. I'm back. Hey.
Okay.
I didn't want to interrupt you there. Sorry about that.
No problem.
My wife's off running some stuff, and it's a holiday, so kids are at home, and my youngest one was told that something was going to get flushed down the toilet or something like that, and she was just freaked out that the cat was going to go down the toilet. I don't know what happened. My kids are playing a joke, and so the 3-year-old takes it literally, and
that's very reasonable.
It's reasonable, yeah.
So anyway, after all that, basically, so what I was saying before you left, Prime, was that the EAX is like, you're very close to the name. It's just the extension of the registers out to more bits.
Okay. Yeah.
A was 8-bit, AX, and then it extends to AL, AH, the two high and low part. Then it was AX for 16-bit, EAX for 32-bit, and it went to RAX for 64-bit. In fact,
yep.
I don't know if I could probably show you that here if we, typing day. If we try to get like you went 64, like a 64-bit integer here, where I'm going to return something 64 bits, then it has to do a larger move, and you can see it just changed the prefixes to R, right?
Okay.
Same exact code, but just doing it with 64 bits now, right? Whereas if if these are 32-bit, then I'm going to get the E version, right? And that's just, yeah, that's all that is. So there you go.
Awesome.
Okay. So as I was saying, ABI is the reason why you have this difference. And so what you're seeing fall out here is that in the x86 64 ABI for what I would believe would be Linux in this case, it basically says that the first input parameter is going to go into the EDI register, but the first return value is going to go in EAX. That's how it will work, right? So when you call a function, if you happen to want to return your first parameter, you have to do a move to move it from the register name that's going to contain the first parameter to the register name that's going to be the return value. In ARM, the first return value is also the first parameter value, so it doesn't have to move it. Now, I can demonstrate this by introducing a second variable, right? So now we have a num and a num2. I'm sorry it wraps here, but we're trying to fit a lot of things on the screen at a large font, right? So if I were to switch from returning num1, which is in that first slot, to returning num2, then you can see that ARM has to do the same thing. See? It now has to move, the second parameter will go in this R1, right? But the return value has to go in R0 or W0. In this case, that's again because of the 32-bit nature. You can actually see that will change if I do 64 here. This is again, ARM has the exact same thing going on as Intel. You can see those change to X, right?
Yep.
That makes sense. So there's a lot of stuff like that, I guess is what I'd say. And that's not really a difference at all in the instruction set. In fact, you saw ARM have to do the exact same thing here when we add a second parameter. Now they're exactly the same, right? First, they have to do a move to move the parameter into the return because they're in different places, and then they do their return. Exactly the same, right?
Yep.
Okay. So let's talk about we'll talk about some other differences in a second because there are other differences. But what I want to talk about first is just the difference that probably makes the most or has the most impact, if you will, on hardware design in any meaningful way. And it's something that you can't even see if all you're doing is looking at the basic Godbolt output. Because, like I said, when you look at these, they look basically the same now. So, you know, if you didn't know anything further about what was going on behind the scenes, and you looked at these, you would be like, I don't even understand why people are saying there's a difference between ARM and Intel. They look exactly the same, right?
Yeah.
But there is one really big difference, even to this day, and that is if I turn on in Godbolt here this thing called compile to binary object, what that does is it actually produces the actual machine code. It doesn't produce just the assembly. It produces the actual machine code that you would like literally put in your executable, right? And what it will show when we do that is above each instruction, it will show literally the binary that will get sent to the CPU. Like the actual bits that are in memory that comprise the code, right? That are this code. And what you can see here, even just with this, I mean, this is not even code, right, Prime? I mean, it's like, It's not even doing an operation at all. But even so, we can see a massive difference between these two if we look at the binary that's actually generated. So if we start with Intel, right, the oldest, most venerable architecture that we have, you can see something very striking. The binary is not the same length for each instruction, right? So for those of you who read hexadecimal, you know that each hexadecimal is 4 bits. So any 2 hexadecimal digits is 1 byte. There are 2 of those here. So this right here is a 2-byte instruction. It's encoded as 2 bytes. Does that make sense?
Yes. Yes. Sorry, I was shaking my head, assuming it's yes.
No,
I even
sorry.
know that 4 bits are referred to as
I'm
a
looking
nibble.
at the other screen, so I'm only going by audio.
Oh, okay. Yeah.
Yeah. Whereas the return instruction, even simpler, it's 1 byte. It only takes 1 byte to encode that return instruction, right? So what you can see there is very compact encoding and also variable length. We don't know, like, without knowing what the instruction is, if I were to just ask you, Prime, how many bytes does it take to encode an x64 instruction, the only answer you can give me is, I don't know. You have to tell me the instruction first, right?
This is going in a very interesting direction. Okay. I was about to say I noticed that the other 2 seemed to be the same length.
Oh, yes,
and it's proportional to the architecture that they're on.
Yes, it is.
Okay.
And so if we take a look at what happens when we are compiling in in ARM, for example, right? What we can see is that there are 2 different instruction encoding sizes, depending on whether you picked ARM or ARM64 here for GCC. And part of that is because ARM also defines this thing called thumb, which is a 16-bit as opposed to a 30-bit instruction. You actually could, I believe, force this to have generated 32-bit instructions if you'd wanted to, but that's kind of neither here nor there and getting way into the weeds. So we're going to skip that for now. And I'll simply point out, no matter which one of these you pick, what you will notice is the instructions are very regular now. Although they do have random gobbledygook here in the sense that if you don't know how these instructions are encoded, these are just going to look like a big old garbage set of digits, right? You can easily tell, even without knowing anything else, that they are exactly the same size. In each case, instructions are not differing in how big they are. And in general, with the exception of the fact that, like I said, there's this thing called thumb you can use for compression where different segments of your code can, when you do a branch, you can say whether you want it to be encoded as 32-bit instructions or 16-bit instructions. So there is a little bit of variability in ARM. There is no such thing as this like uber flexible format. And I just want to underscore this a little bit by adding one more thing to the mix, for example. So let me go ahead and change our first parameter into an array here, effectively. Now, if you don't know C syntax, you may not know what this means. This is just a pointer, but we don't care about that. Just think of this as an array, so something that we can access by element, right? And so let's suppose I wanted to add these two together, and I'm going to go ahead and well, you know what? Let me simplify just to not do too many changes at once. First, I'll just add just an int here, and we can get rid of these types because we don't care about that anymore. So we'll just use, basic, whatever the default integer is. We're just going to add two numbers together, right? That's all we're going to do here. And what you can see here, and unfortunately, this compiler is getting pretty creative on us and using a shorthand syntax for addition. What you can see on the ARM side is pretty basic. We're just going to have an add instruction. This is an add instruction, but it's kind of a creative format for the add instruction that puts the add in here. But effectively, it is doing the same basic operation, and that's fine, et cetera, et cetera. All I wanted to show was we can make these bytes get longer up here. Now we've got a 3-byte instruction, right? 1, 2, 3. Before we only had 2, so it gets longer and longer, right? Maybe now I've got, I do want, let's say I want to change this one to an array, like I said, and I want to access, some part of it, right? We can make this even longer, right? If you can see, it grows and grows and grows, right? And so the x64 instruction set, no matter what I do, I'm never going to get longer than 32 bits over here for the most part, right? Like, in general, it's just going to add more instructions when it needs to do something. But Intel has this sort of flexible format where it can do a bunch of weird stuff where it can just make the instruction arbitrarily longer if it needs to, and you'll pack more into a single operation, if that makes sense. So that is a very big difference between these two. Now, again, and I'm happy this happened so I can actually point it out, you can see there are some circumstances where you have 2 of something, right? In this case, you can see this was encoded as 2 things. Like it was 2 pair, it was 16 and 16, right? So there are some times in ARM where you can say, I'm going to take 2 instructions to encode 1, basically, if that makes sense. But it's still highly, highly regular. There's none of this like, this one's 6 bytes, this one's 2, and this one's 1. Nothing like that really happens in ARM for the most part, right? Not at that level of granularity. And so, why do I say this is the biggest difference that actually matters at the hardware level? Well, the reason that this matters so much is because if you think about what happens here with this, imagine you're the CPU and you're trying to execute these instructions. You have no way of knowing. Like literally, you have no way of knowing when you're on a particular instruction where the next instruction is, right? You have no idea because until you actually parse this instruction, it's parsing, right? Like it's like you were handed a text file that had like, you're trying to parse identifiers in a text file. It's got some number of characters makes this identifier. You don't know where the next token in that input stream is until you count how many characters follow each other and find a space, right? Well, the same thing is going on here. The instruction encoding defines a bunch of things like, oh, if this bit is set, then read another byte, right? And so the processor has to actually parse each instruction completely before it knows for sure where the next instruction is.
So does it have some sort of like peak, kind of like whenever you're doing tokenizing in a compiler, something similar to that where you're like, or does it know by the very nature of the instructions that this one's the last one, or does it have to peek at the next one? No, it's not. There's nothing left in it.
So the way that this actually ends up working in practice now is even more wild than what you would think of as happening in a normal parser. What these CPUs need to be able to do, and we kind of talked, I think we may have mentioned the concept of IPC once on your stream. I don't remember, but The modern processors get most of their performance from this notion of instructions per clock. They get performance by doing more than one instruction every clock cycle. So when your processor says something on it, like this is a 5 gigahertz processor, that means, well, the clock is running at, 5 billion, ticks per second. And the CPU, in order to get performance, isn't just going to try and execute a single instruction on each one of those clock cycles effectively. It's going to try and execute several, right? At least 2 at a minimum, but now they're trying to push up, towards 6, 7, 8, right? They're like, it keeps getting more. What that means is in order to sustain that, it has to be able to parse. We call this decode, right? It's not really called parsing, it's called decoding, but it's basically parsing on Intel side. They have to be able to decode more than one per cycle. So that means every clock cycle, the CPU has to look at something like this move add ret going on here, and it has to try and decode them all at the same time in order to get it fast enough. So what it actually does is it guesses. It uses some knowledge of exactly how the things work to guess about probably where the instructions are, and then tries that. And if it succeeds, you get the maximum number of instructions decoded, right? And if it fails, you maybe get less. I'm serious. That's how it works. It's like sort of a best case kind of thing where it's like, well, hopefully we can capture most instruction streams most of the time by guessing these things and having circuitry that tries that to code. And then, so if you thought about this in a parser sense, it's like you guessed how long the identifier was going to be and ran a couple guesses in parallel and then checked at the end to see which one was correct.
Dang. Yeah, I don't even... Right. That just sounds difficult in my head even to create, but I assume it's all hardware logic, as in it just knows how to, whatever, the bits are magically flow to each box, and each box takes some sort of variation guess to it, and one of them comes out correctly, and boom, you got it.
Because once you're done, you know how long it was, so you just go like, hey, was one of these guesses correct? And if the answer is yes, you're like, sweet. If it's not, you're like, oh, well, then we still ran the slow decoder that only gets one instruction or something, and that one will be the one we use, right? So the reason why that matters is because as your head just intuitively did, where you're like, oh, God, right? That's not pretty. That is a serious architecture thing you've got to deal with. Contrast that to if you want to do that with this instruction set, let's say ARM64. Well, guess what? You know exactly where they are.
Yeah.
Right?
Yeah, precisely.
Every 4 bytes is a new instruction. I want to decode 4 of these in parallel. I just start every 4 bytes and I decode them. Done. Right? I didn't need any complex logic or fancy footwork going on there. I just copy my decoder 4 times and feed it 4-byte offsets, and then I've got a 4-wide decoder. Happy birthday, right?
A quick question on that one. Is this part of where the energy savings, there's no additional cost for decoding at each one of these steps, or is the decoding cost of parallelization is significantly less than doing it one at a time? Is that where we're going with this?
Yeah, so I don't want to claim that this is some kind of a definite thing where it's like, oh, well, obviously then you will get lower power out of ARM.
Okay.
I merely want to point out that in terms of when you think about actually implementing one of these chips, how much space and how much power are you going to have to dedicate to decoding?
I see what you're saying.
Well, okay. This is a real difference. So if someone wanted to make the claim that ARM was more better for designing a more efficient chip, they could certainly point to this and say that's a thing, right?
Yeah, it makes it much simpler at least to talk about this at least, because everything's a fixed offset. My small pea brain can understand that. I can't even think of the magic behind Intel to make whatever that is, where you could have up to 6 bytes to explain an instruction. How do you jump ahead and guess that? It just sounds magical to me.
And I think you're not the only one who has trouble conceptualizing that as well, because it takes them a long time to improve the decoders on x64. Like, a lot of work goes into it. Whereas as far as I know, there's no magic to decoding lots of instructions on ARM. You just do it, right? It's like no one had to be clever. Yeah. They just did it. So I think what you're experiencing there in your own brain is basically what they experience in hardware. It's like, okay, this is a serious thing, and I've got to go do actual work on this, as opposed to just, oh, we want a wider decoder. Well, then we just decode more, copy the decoder more times or something, right?
Does this lead to
and I'm
larger
sure I'm
binary
simplifying
size?
that a bit, but
is this
sorry?
like a holdback? Because x86, I assume, is older than ARM by some amount, and
Yes.
that
Yes.
binary size used to be like hyper important comparatively to it is now. Is this also like a binary size implication where they had to get clever at one point in time, in which that cleverness maybe has left some level?
Yes, everything you just said is true. And it's more than just binary size. It's also speed. And that's actually still true today. So let me talk about that. So if you move yourself back in time to something like the 8086, every byte you read from memory was expensive, right? Every single individual byte was very expensive and you waited for it. So what that means is that if an instruction can be encoded more compactly, like if you could encode an instruction in 1 byte instead of 2 bytes, you got faster. You weren't just smaller, you were faster, right? And so there was a lot more incentive at that point to encode smaller binaries. Now, fast forward to today, and you might think, well, it doesn't matter anymore. Turns out it really does, actually. And the reason that it matters is because, especially with the way people program nowadays, where they've just got these massive, everyone uses 50 million libraries, even if the libraries have the same exact stuff in them. There's 17 different JPEG.
Let's go.
Yeah. It's like how many JPEG decompressors are in the thing you shipped. And usually the answer is I don't even know, right? Yeah. Several probably or something, right? Because they just get included from everywhere and who knows what, right? Or things like that. How many copies of the entire Chrome browser shipped with this binary? It's like 4, right? So anyway, you get these things where the code size is very large. And one of the things that's actually kind of amusing these days is actually this does create a problem. It creates a problem for something where there's this part of all modern chips have this. It's called an instruction cache. And basically what its job is to cache things just like a data cache caches the data your program's working with. The instructions have to be cached as well because it's expensive to bring them in from memory. Just like it was in the 8086 days. The more things change, the more they stay the same. So having giant binaries means you have these things called I-cache misses or instruction cache misses, which are when you're jumping all around through giant, massive heaps of code, and you end up stalling because the processor is literally waiting for whatever random virtual function call you're calling on your object-oriented mess to come in from memory and get there so it can execute it. And it's just sitting around waiting because it ran out of things to do, waiting for your code to come in, right? And that's a real thing that happens nowadays. So amusingly, even though you would think this doesn't matter at all anymore, code size still, oddly enough, matters because the I-cache is only so big. You may only get 32K of I-cache or something, depending on the processor. And so the more code you can fit in that 32K, the happier you are. And so it matters. Now, does x64 necessarily do a great job of maximizing that space anymore? Not really. And that brings us to our next point. So one of the things that artificially hurts Intel as opposed to ARM is normally if you were to design an instruction set that did this sort of thing, what you would be doing is studying your modern instruction streams very carefully, and you would be planning almost like, for those of you who know compression, almost like a Huffman tree or something. You would be planning exactly how the bit layout worked for your instructions, such that you would minimize the size of your typical instruction streams. It'd be like this, it's like designing compression format, right? Yeah. It's like, I'm going to pick this and I'm going to see how well it does at compressing these things, right? But Intel didn't do that, right? Maybe 8086 had a little bit of that, right? But over time, as they've extended the instruction set, what the variable length ended up doing more than anything else was just allowing them to add instructions while maintaining backwards compatibility. That does not lead to the most concise encoding for an instruction set, because now you've got extra bytes that are all over the place that were really just there to signal like, hey, we're using some extended instructions now, right?
So what you're trying to say is that in the backwards compatibility effectively made it such that in Huffman, for those that don't know, Huffman trees effectively just the thing that appears the most takes like 1 bit to encode. Whereas in this world, you're saying that the things that take 1 bit to encode are the things probably, or when I say 1 bit, 1 byte encode, shall we say, if that's even true, those are the least likely to be used instructions effectively, other than maybe return remaining the same, but the rest being like, no one's using an 8-bit add, therefore 8-bit add just sits there in some 1 byte range and it's just like, well, I guess I'll never be used again.
Effectively, yes, and it's not as bad as maybe what you said. Meaning it's not like you pointed out correctly. Return, right? That's commonly used and still 1 byte. That's great, right? So it does get something from it, but my point is more it's handicapped, right? At that point, like like in golf or whatever, right? It's like it's getting an unfair detriment to it because it wasn't designed for that. So it's at this point now where if you imagined redesigning x64 to be optimally encoded for space, and you could even throw in efficiency of decoding. You could do things to make it much easier for the decoder to know. Like the first byte always tells you how many instruction bytes there are in some way, so that you can do a quick spread to know where to gather.
I was gonna say that. I actually even thought about that. I was like, dude, you could have the first nibble really be like, this thing's gonna be 1 to 16 jumps, right?
Oh. Yeah, and it's a little hard of that because you probably need to encode how big several instructions are. But I mean, I don't want to pretend I know how the hardware's going to work. I don't know those things, right? So I don't know what would help them. But point is, you could consider those things, right?
Yeah.
And you could make something that minimized space while still keeping decoding reasonable. And my point is just x64 is not the best representative of what you could get out of a variable length encoding. So it's a little unfair also to say, well, we could compare x64 and ARM and conclude that ARM that fixed length instructions are always better because ARM is better at low power or eventually better at high power, or who knows what, right? Not really, because x64, a lot of what its benefits were backwards compatibility, which is very valuable. It created this really great ecosystem over many generations, but that's more what it was coming from. So you could also say that one of the great things about a variable length instruction set is they've never had to wholesale wipe it, really.
Yep.
And so that was great too, but again, not something you necessarily care about if what you're talking about is how low power can things be. You're not talking about those other important benefits, and so again, you get less of it. So anyway, so that's really the biggest difference that you'll see from a hardware standpoint. I want to talk maybe so are we all good here? Is that I don't know, I can't read the chat while I'm looking at my screen here, so I don't know if everyone's okay with that. But
chat's going great. A lot of people have a lot of opinions about stuff, but it looks like it looks great. We're doing good, so we can move on to the next thing. I think people largely get what's happening.
Okay, a lot of people. So people are arguing about ARM versus x86 or something like that in there.
Actually, the explanation on this one thing, they happen. So don't worry. There's always someone.
Oh, well, that's fine. If someone wants me to elaborate on something because they don't feel like it was correct, we can also do that. Was there something in particular?
No, I'd rather just keep going forward, honestly. Okay. There's always some highly, because then we'll just be so in the weeds on one particular edge case, in which you do go, hey, not everything's like this, but this is generally a nice, way to go.
Yeah, I mean, that's always a problem with things like this, is it's like, well, anything that I say, there's always this, and that's just,
I assume that's true in my head, so I just assume that chat also adopts that mentality, which is, you're obviously, first off, you're talking to me, a Neanderthal, comparatively, so therefore it's like you're already boxing up something, and we don't have hours just to spend on every particular point, so let's just move as fast as we can, get as much understanding as we can. Everybody is slightly, the veil has been slightly pulled back, and now we see a little bit more,
Okay, well, yeah, if anyone wants to follow with me afterwards, that's fine too.
Yep.
But either way, so anyway, you can kind of see here exactly what's going on with the encoding bytes, and that's a difference. But like I said, it's unclear really how much advantage that actually is for something like ARM. It is true. So let's move on to maybe some things about power. So it is true that traditionally ARM has been much better at low power. And so when we're talking about just in practice, where has the low power stuff come from? ARM is way stronger at that and has way more examples of excelling in that domain than something like x86 or x64. And this was true, my understanding, although I was never involved in I never had one of these computers as a kid, but my understanding was this was true right from the first ARM 1. So the original ARM that they designed as a successor to BBC Micro, which I don't even know what chip was in there. I think it was a 6502 maybe, or I don't remember what was in the BBC Micro because I never had any of those. But they designed it as a new chip for Acorn computer. I think that's what the A originally stood for in ARM, was Acorn, believe it or not. I could be very wrong about that. I'm sure chat will correct me if I'm wrong on that one. But the original chip was extremely, extremely low power. Like, I want to say there were weird anecdotes about it running. It was able to run while not being powered.
Someone literally just said, yes, the first ARM was notorious to consume 0 power. And I wasn't sure if that was a joke, as in it was crashing, as in it just didn't run, or if that was saying literally it just would run with such little power that it was
literally. The anecdote anyway, and again, I wasn't there. I don't know any of this stuff. So I'm just saying what you read when you read about ARM history is what it will say. Supposedly, just like the residual electrical fields from powering the other things on a circuit board around the ARM chip was enough to make the ARM chip work.
That's incredible. That's
it was
cool.
0.1 watts or something. I don't remember what the draw was on this thing, but it was so low that you could run it without actually intentionally powering it. That's the anecdote. And I have no idea if that's really true, but that's the anecdote anyway. And who knows? I am not an ARM person, and I don't study ARM history, so that's for someone else to say. But that you will see that claim, right? And so it comes from a lineage where they were intentionally designing this thing to be a low power chip and succeeded, right? So the chip they actually shipped as the first ARM was very low power. Now, originally, there's all kinds of weird claims, and some of them are actually false. So, for example, it's typically claimed that ARM 1 wasn't microcoded, right? So there's this notion. So if you look at something like the early chips, right? There's a 6502, the kind of classic chip that people refer to for the old microcomputer days, that it does not have microcode, meaning the instructions are directly wired. When it loads something from memory, the bits are wired directly to the instruction execution matrix. There's no intermediate, right? Probably explaining this poorly, but whereas if you take something like the 8086, it's microcoded. What that means is that each instruction, and not every single instruction, if we have pedants in chat, I'll try to be more specific. Not literally every instruction, but almost every instruction on 8086, 8088, so think original IBM PC, doesn't actually directly feed the instruction bits into the execution part of the chip. Instead, those code for a location effectively an internal ROM, if you will, that says a series of smaller instructions to do. Typically, 2, 3, 4, 5, right? So if you go back and look at original 8086, every instruction actually maps to some series of smaller instructions, which we would today call micro-ops, although I don't know if they called them that in those days. So people normally said, this is what I always heard anyway, was that the original ARM chips were not microcoded. They were RISC, reduced instruction set computer, right? And they were directly mapped just like a 6502. But that apparently isn't the case. I actually saw recently, just in the past, in recent memory, not in the old days, there's a fellow called Ken Sheriff who does these really great reverse engineering of silicon. They actually reverse engineered the entire ARM 1, and it's microcoded. You could argue that the microcode is less microcodey. It's a little less microcodey than something like an 8086, But to my eye, I was like, that's microcode. Like, it is definitely, I would consider it microcode. And so even originally, and this is, I always try to spread this around because a lot of people think like original 8086 was much simpler. Original ARM one was much simpler. Even the original early chips, they were using things like microcode where instructions map to micro-ops effectively. So where do I want to go with that? Well, over time, this kind of thing just gets more and more and more common. And so today, when you look at a modern ARM chip, like something like a Snapdragon or an M-series chip, if you look at something like an Intel chip or an AMD chip for x86 or x64, they all work off of the same basic model. And that is a fairly complex instruction set comes in. No matter who wants to tell you that ARM is RISC, it's not. There's nothing reduced about having hundreds of instructions in your instruction set, right? The original ARM had something like 41 or something like that. Modern ARMs have hundreds, right? So they take a fairly complicated instruction set in, and then they execute a series of micro-ops, just like their original forebears did. But now those micro-ops are going through a much more complicated series of scheduling and executing parallel and all this sort of stuff, right? They all work that way. And there really isn't that much of a difference between the chips at that point. It's just who does a better job implementing them low power wise. And it's hard to really find things like I have never found somebody actually been able to pinpoint beyond the difference in decoders, which I think is real. Like the decoder can be much more simplified on ARM and still decode lots of instructions at the same time in parallel. I have never seen somebody identify, oh, here is a particular aspect of the ARM ISA that allows it to be way lower power than Intel, right? Maybe I've tried to highlight one of them, which is the variable length instruction. Maybe you can get something there. Another one is just, well, when you say x64, you're probably meaning all of the backwards compatibility baggage. So that could take up, some extra space in terms of microcoding ROMs and maybe some things like that. Maybe the memory model. There's a few things like that. But it's very hard to identify anything in the ISA that's like, well, there it is. Like, that's the reason that ARM is so much more power efficient. So for me anyway, the reason I usually think that ARM is more power efficient is actually business related, not anything to do with the actual ISA. Could there be some things that maybe are an edge for ARM? Yeah, but they're like an edge. I think the real reason we've seen ARM be so successful at low power while x64 hasn't been is just because of market dynamics. ARM grew up in low power. The companies who licensed ARM were all focusing on low power. And more to the point, there are way more of them. Because it's an open platform that anyone can license, you had way more people trying to make innovative low power designs, right? Whereas if you look at what happened with x64, there's only 2 players. And they were never really that focused on low power. They all came from higher power and then tried to start low power initiatives, which they're now working towards. And so I think the history makes it seem like ARM was magically better. I don't know that it was. I think that may have been just more of an artifact of what the original, when you think about how chip design works, you get a lot of legacy stuff going on and a lot of well, we've already got this design and we're low risks. We don't want to take a wild risk with every generation, so we're not going to change it that much. I think what you're seeing is mostly inertia, to be completely honest. And yeah, could there be some things like the decoding or some backwards compat badness or things like that, where at the limit, ARM is actually better for low power? That could very much be true. But that minor element of it, I think, is not why historically it's been the lower power thing. There was also some things earlier on that would make interrupts were more power efficient in ARM right from the start. But again, that was very early. And I don't think that is something that you would carry forward to something like, 2010 or when people normally think of ARM being low power. So that's usually my feeling on it, is it's overstated. The degree to which the ISA is mattering here is overstated. I think it's more about who was working on what and how much human creativity was brought to bear on each side for doing low power. and how those market dynamics work is more why we've got this entrenched version of ARM. Whereas I think if it was just ISA differences, might there be a difference? Yes, but the difference wouldn't have been as massive as what it was at the time. Does that make sense?
That makes perfect sense. I mean, you see this in virtually every form of life, even regarding, you can disregard every last technical problem you've ever experienced. Just company cultures dictate different types of work, different types of how people assimilate and work together. You know, so you can see this, that when there's a certain need at a place, everyone aligns around that need and they work towards it. And so it's like, it makes perfect sense that if ARM has always historically been in the low power, it makes sense that they build architectures and chips that are just thoughtful first of low power versus Intel has always been like, this is the fastest desktop. You know, like that's kind of where they were birthed, is like the Pentium 3 had the Blue Man dancing around for 400 megahertz. And so it's like they
and
must
data
be,
centers and all this stuff, right?
They're trying to maximize how much power, I assume, trying to get through it. And so that's a very different problem. And I assume that solving one makes it difficult to solve the other at the exact same time. And so I could understand this. At least minimally, it's a challenge. It's a tough, like thought pattern to change in an organization.
And I think, like, one of the reasons that I feel like my analysis there is not like completely BS is just because now that you've had 15 years or so, or 20 years of Intel and AMD going, oh, we probably do need to care about low power, right? Because they sort of have changed direction, right? They're producing some fairly competitive low power chips now, right? And so the fact that that's happening suggests to me that, like, and again, you can't turn on a dime with hardware, right? If you've got a lineage that you're maintaining, it's not like you can just wake up one morning and just be like, all right, the whole company's about low power now. Like, that's not how that's going to work, right? 20 years is not a long time in hardware, right? It's a long time in software because we can iterate so quickly. It's not a long time in hardware. And so moving those organizations, and they have to be risk averse, and they have to continue to sell to their high power customers. So they can't just take all their engineers and say, okay, we're just going to ghost ship the high power parts. Like, that can't happen, right? So with limited design resources and all those sorts of things, you only have so many great architects at your company, whatever. I think that what you're seeing is a lot that. And so again, that's not to try and state that there are no differences in the ISAs. I've tried to point some out, or that those differences won't be important at the limit, or even that they weren't important during that process. It's just to say that I think what we saw was a much more exaggerated difference between the two because of business effects. And by the way, I think in some sense you could say there is a property of ARM's ISA that makes it much more low power that is not often mentioned, and that's that it's open license. I bet if x64 had been an open license, they would have had better low power chips. Why? Because some other chip designers at other companies, maybe even Apple, maybe when they did their chips, they would have done it. I mean, they probably wouldn't have, because they had their iPhone line, which would have started on ARM. But, who knows? You may have gotten other people who were like, wanted to do low power stuff, who were really great at it somewhere in the world, and they would have licensed x64 because they wanted to tap into PC market or something and ship low power PC devices. So in a way, I would consider ARM's openness to almost be the most important aspect of their ISA for low power, beyond all of the things that anyone else might say, right? Does that make sense?
That makes perfect sense. A lot of problems in the world do come down to a people problem. And so this would not be shocking that if this actually just turns out to be the answer, that you end up in the end having just equally competitive chips when the focus becomes on low power, and that's just the way it is. So I mean, it makes perfect. It does make a lot of sense. I think you also made a good argument about not having to guess the variable length. Therefore, you could always have a fairly consistent decoding, and thus you don't have to try as hard. And maybe there is just something there where you're like, we only do 4 instructions ever. We don't have to think about trying to hop 6 or 8 or 10 and do anything super clever. We can just do it, and that's it. So I can see that also being very, potentially beneficial. Maybe, but I'm so layman at this point that it's ridiculous.
But
I know
I
Kirchhoff's
think
law, and that's it.
It matters. It matters, right? I think it does matter because it just makes it much more difficult for the Intel side for the x64 side to scale that decode. And when you're talking about, like, literally chips are now talking about, we want to decode 8 instructions at a time, things like that. That's really hard if you don't know where the instructions are, right?
Yeah.
And so when you look at something like ARM, there's a definite advantage there. And like I said, I don't want to minimize that because we don't know. Like we don't know how that could play out in the long run. It could be that it really is important and off you go, right? So
Yeah, because I would assume to be able to decode that many up ahead, you'd need a larger variance of just things that can just test run various attempts at decoding. Thus, the ARM one's only going to be 8 because that's like, well, 0, 4, 8, 12, 16. Like it can just be like, here we go. I'm going to do all at the exact same time.
yeah,
Versus
and
Intel's
yeah.
doing this like magic, like, okay, we actually have 16 lines of that going, which theoretically that has to consume more power. Just by pure,
Yes.
observational power.
And there's other weird things that are happening now where like sometimes they don't have what's called a micro-op cache, which is where you have a thing where you decode things into a cache so that that you don't have to do that decoding again for like hot loops and things like that. And so you look at things like that and you're like, some chips now don't have that. Like amusingly, it's the x64 chips that oftentimes now don't have a micro-op cache, even though they used to. And so you have to consider things like that might get easier too for the same reason, because now again you're decoding all the time and you're not using that cache. I don't know. So there's a whole bunch of things where like decoders are putting more pressure. You have to have much smarter designers working much harder, I think, to deal with the x64 side of that. But does that end up being a real crippling factor for low power? I just don't know. And again, we are seeing Intel and AMD make some pretty impressive gains there. And so at some point, it may just be like, no, actually, they managed to figure it out, and it doesn't really handicap them very much. And if we're talking about 0.5% or 1% or something like that, that only matters at the very, very limit. If everyone else did exactly the same stuff exactly the same way, you would get a little bit out of it, right? But it's not going to be 10%, 20%, twice as fast, half the power, any of that stuff, right? So, that's my guess, but it's just a guess.
I can't believe we're doing all of this just to run JavaScript. I mean, who would have thought, huh? Society, if.
Well, the hardware companies love it. I mean, they want you to run JavaScript, because if you were to start using the chip very efficiently, how do they sell the next chip, right?
It's very, very true. Ginger Bill currently in shambles right now as you say that.
I'm sure they don't want to help him at all, right?
Yeah.
They don't want to hear about that. They want to hear about JavaScript. It's like, tell me more about this JavaScript. Yeah, I mean, so anyway, I didn't want to leave anything inaccurate for chat. Like I said, was there anything people were particularly unhappy about? Because we can go over that in more detail just at the end here, because I think we're mostly
we can call ourselves done, if you will. But here, let me just, I'll make you small. You can go back to regular Casey, and I have all the chats up. And if any, my guess is that there probably isn't much. Everyone seemed to be very, very happy with it. I think there's just some small things around. Just at very, very tiny points.
Like an ARM thing or something. Because again, I should also mention, since I don't do ARM every day, I'm not even gonna know some of the small things to mention as well, which would be true, because it's something that I only look at occasionally, whereas x64 is really where I live. I probably should learn more ARM natively, because over time it becomes more important. But is there anything in particular people wanted to mention, or just get in the stream so that it's not inaccurate?
A lot of people are just saying they're having side discussions about what was being discussed. They're just kind of going into bigger and smaller things. A lot of people, apparently there's just a giant, even new, crazy DHH drama. I saw a lot of that happening. Matt apparently went after DHH, and it's gotten insane out there. But here,
so while we were talking,
while we were talking, new drama dropped. I did actually grab both of them right here, and so I was gonna look at that here shortly. By the way, if you want to go back to a full camera mode, you won't be a tiny Casey in a tiny box.
Let's do it.
Let's see. The only ones, I guess, there's a lot of. Let's see. Can we ask Casey some questions? I don't understand why hundreds of instructions exist. You have an add. Let's see. You have an add a 6 bits constant. It makes sense to use a literal encoding in these bits in the instruction, so you don't need to decode these bits. Okay, hold on. I'm a little bit confused. I had a lot of questions in this thread. Okay, there's a lot of questions apparently in some sort of thread. Oh, look at this. Oh, I missed it. I've never seen something like this. That's why I was reading it all goofy. So a lot of
Okay.
questions in this thread. Says, here's some questions.
Okay.
Let's see if I can find anyone that that is interesting. So first, why do we have so many instructions? Why do hundreds of instructions say exist in modern like ARM processors? I understand, we at least understand some of the x86 stuff. There's a lot of historical reasons. You have add 16, add 32, add 64. Dropping any of those, why do all those exist? Why are there so many instructions? If that's an appropriate question.
It's an appropriate question, and I guess it depends. The real answer is a lot of reasons, right? But I can give you an example that hopefully will let you imagine all the kinds of reasons there are. So CPUs have gone from being single instruction, single data, right? So add one number to another number. They've gone from that to single instruction, multiple data, which means you could do adds now, and you can do them by, wide. So 4 numbers added to 4 other numbers produces 4 results, right? 8 numbers added to 8 other numbers equals 8 results, and so on. These instructions add to the bulk. So if you thought that you needed 40 instructions to do all the things you were going to do on individual numbers, well, you probably need at least 40 more instructions to do things on the wide versions. And you might, if you added them in different ways, you might actually have multiple copies of those instructions, because you've got like the ones that are 4 wide and the ones that are 8 wide and the ones that are 16 wide. And then you also have all kinds of new things that are about how to move things between, themselves. So one reason is just processors went SIMD. Another reason is anytime CPU designers are looking at what their customers are doing and looking at benchmarks, they're often saying things like, well, okay, we could get way more performance on this very common, very important benchmark if we had an instruction that did this. Loaded 4 values and put them into 2 different registers in this way, or something like weird
There's
stuff,
some
right?
statistical, like this one operation just keeps happening because it turns out left pad does this one thing and the universe runs off left pad. And so it's like, here's my super and special instruction for this one common use case.
You get those, and those are there because they're trying to they're trying to maximize that benchmark. And so even though that's not a smart instruction to put in an instruction set, it doesn't make sense from the perspective of, we want a nice, clean, simple design for this chip that only does a few things, and we want to minimize what people have to learn and what the compiler has to output. And all that. They're just like, look, we need this instruction or we'll perform bad on this benchmark, so it's in there, right? And they know that. They don't want to put that in there. They know that it's like kind of clumsy, and that's like but that's what they need. This has gotten horrible, especially with things like AI, video encoding, string search. There's all these special purpose instructions that are just there to speed that up. And ARM has to do that too. They can't not do it, right? They can't just be like, no, we're simple, because they're trying to compete with Intel. They're trying to compete with PowerPC. They're trying to compete with RISC-V, whatever it was, whoever it is at the time. There are people out there doing other ICEs, and ARM is in a licensing business. They have to have ways that people can, use their standard instruction set and get good performance. So if you take something like ARM, now it even has 2 entire instruction domains for those wide kinds of instructions I'm talking about. There's a thing called Neon, which was the original wide instruction set for doing those, multiple things. That's a whole new set of instructions that adds to the total. They added a new one that's a vector instruction set called SVE, which is a variable length vector instruction set. So that's a whole nother set of instructions, completely different than Neon, for doing the same thing. And that's an ARM, the supposedly RISC, right? Which that's why I say it's ridiculous to call it RISC anymore. It is not RISC. It is incredibly complicated, right? And we didn't mention this in the actual meat of the stream, but I'll say it here just in case people are wondering. Some people have retreated to the concept that what RISC actually means is just, can you do a memory fetch along with instruction or not? And that's it. Called a load store architecture is often what this is called. Nobody would have claimed that's what RISC was originally, so I don't consider that to be valid, because it's even the name, reduced instruction set computer, there is nothing in there but reduced. There's no claims about it. It happened that at the original ones that load and store were separate. Why? Because that's how you reduce the total number of instructions, by not having all these permutations of, I can do an add from register or an add from register to memory and all these other sorts of things. So in my opinion, that's not really a valid use of the term risk. But if you wanted to just ignore the risk-CISC debate or use that and just ignore it, it is true that ARM is much closer to a pure load store architecture than Intel. Intel, and we didn't really go over this when we had the stuff up, but I'll just tell you, it can still do things like, I want to add this register to this memory location, and it will read the memory location and add it to the register as one instruction that's encoded.
Yeah,
it will
I
do
feel
it
like
as
we went over this last time with the x86 needs to die. You showed me like, this is memory to memory, constant, variable to variable, right? Like you had all these different kind of
I think they got rid of memory to memory, but yes, the original 8086 though did have actually had memory to memory. And so if you look at that, if you looked at that and said, forget RISC, just think load store architecture. ARM, you could say that about it. It's like in ARM, generally speaking, most of the time, your loads and stores are individual instructions that you see. They cannot be baked. The loads cannot be baked into instructions. Whereas on Intel, loads can be baked into other instructions. So I'll just throw that out there as well. That's a side point. But anyway, hopefully that's where do all these instructions come from? They come from processor manufacturers thinking they got to target something and doing that thing. And then the other place is system control stuff. Modern systems are very complicated. We got all these additional things. The CPU needs to enter a lower power state right now. There's got to be structure for that. The CPU has to wait on a change to a cache line and enter a low power state until then. We got to have a structure for that. We got to transition from this security ring to this other security ring. Things that you never would have thought about in a home computer maybe are now, all those instructions have to be there. And ARM has to have them. ARM has to be able to run the same kinds of security rings and memory protection and all these other sorts of stuff. So, you get a bunch of instructions for that kind of crap too. And it's not nothing, right? That piles up. So that's where all these instructions come from. Targeting benchmarks, expanding the capabilities of the processor, and just, system maintenance, system op stuff. Hopefully that answers the question, but
yeah, no, that is a great explanation. And again, that makes so much sense because in any form of software I've ever developed, as time went on, you have to just put stuff on top and you can't just clean break. So it's just like this already exists in my mind and it exists in everyone's mind in this chat that this is just a regular way of life. And
it's worth remembering that nobody is hardwiring all those instructions, right?
Yeah.
They do have a cost, yes, but it's not like the actual core of the CPU has a bunch of actual circuitry to do those specific instructions so that you actually have, if you have 10,000 instructions, you don't have 10,000 little parts of the chip that each execute one of those instructions. It doesn't work that way. It's microcoded. So basically all of your instructions that aren't very basic, like add or something, are actually just doing lots of little mini instructions to accomplish that weird system control thing that you were doing, right?
Yeah.
So the cost for having a lot of those instructions isn't very high. You care more about the decode implications of them, probably most of the time, than the microcode implications, because you just don't care. You're not typically executing those weird instructions. They're not the bulk of your hot loops or anything. So it matters less that there are a ton of instructions than people would think, because of what a lot of those instructions are just not that critical. That's what I'd say.
Nice. Well, I really appreciate having you on here. This was absolutely fantastic, and we should. I'd like to set up some sort of more formalized Q&A in the future. If you want to do another thing, if you want to talk about any other topic, just let us know, and we should do another kind of fun one of these, because this was just absolutely fun. Again, this is just the side of the computer world I never get to learn about. Just not due to desire, but just time. How it all goes. We all have our areas of focus. So absolutely awesome. So appreciate that.
Well, I'm happy to come back anytime, as you know. So, maybe just whatever the chat wants. Hopefully, like I said, there's some things I just don't know anything about. So if you want to ask questions about the ARM instruction set, I can't help you, right? Because if you want to ask questions about x86, I got you covered. So it's usually as long as it's something I know about, I'd love to come on. I always love the stream. It's fantastic. So I love the invitation anytime, really anytime.
Okay, cool. I'm glad to know that, because that's why I invited you to begin with, because I was like, I need to book Casey back.
Anytime. Anytime.
Sneak him in and just bait him with some sort of odd open-ended question. Tell me the difference.
No, I'm happy to come and just hang out and watch you explain this ridiculous WordPress stuff. So I love the stream anytime, really. I love the chat. Everyone's great. So thanks for having me. And anytime you want me back, I'm here.
Okay, I will. I'll get chat to come up with some good questions. Also, TJ says we should have you just on the top shelf, where we actually come up with more in-depth questions than as opposed to just like topical, but more just like how'd you get here kind of questions. The bigger pictures of who Casey is, because I think that would be a lot of fun. So we'll have you come on for that as well, if you're okay with that.
Sure, anytime, literally.
Awesome, love to hear it.
Well, thanks, Prime.
All right.
Have good luck with DHH and Matt.
Whoa. Before you go, we can't forget the most important part. It's computerenhance.com, correct?
If you want to find me, computerenhance.com.
You got to go. Don't be a loser. Be a winner. Enhance that computer.
Yes. Zoom in.
All right. Well, thank you, Casey.
Thanks, Prime. Have a good one.
Bye-bye.